It's been a while since we did a proof here. So let's do a proof, shall we? Let's show why there are an infinite number of prime numbers of the form 4k plus 3, where k is some non-negative integer. Now let's be careful here. We're not saying that every number of the form 4k plus 3 will be prime. For example, 15 is not prime. But what we are saying is that the list of prime numbers, where each prime number is of the form 4k plus 3, is infinite. So to prove that, let's use one of mathematicians' favorite tools, the proof by contradiction. So let's suppose there are only finitely many number of primes of the form 4k plus 3, starting from p1, which is basically 3, all the way up to p sub n. To make things a bit simpler, let's reformulate that as a finite list of primes that are all congruent to 3 modulo 4. If you're unfamiliar with that notation, 3 mod 4 just means that the number will leave a remainder of 3 when divided by 4. Now before we move on, let's make the following two observations. The first observation is that every odd number is either 1 mod 4 or 3 mod 4. And the second observation is that if you take an odd number that is congruent to 1 mod 4 and multiply it by another odd number that is congruent to 1 mod 4, the product of those two odd numbers will also be congruent to 1 mod 4. That's basically because 1 times 1 is 1. All right, with those observations out of the way, let's form this following number n, where n is equal to 4 times p1 all the way to p sub n minus 1. We'll consider two cases. The first is if n is prime, and the second is if n is composite. Now, after a moment's thought, we should realize that n is congruent to 3 mod 4, because this product, 4 times p1 all the way to p sub n, is congruent to 0 mod 4, because it's clearly divisible by 4. So then by the division algorithm, that must mean n is congruent to negative 1 mod 4, which is the same thing as being congruent to 3 mod 4. Now, let's suppose that n is prime. Well, then we're done, because we have successfully constructed a prime number of the form 4k plus 3 that is not in our original list of primes, p1 to p sub n. So that must mean our original list of primes must not be complete. Now suppose that n is composite. Well, from our second observation earlier, we can conclude that n must have at least one prime factor that is congruent to 3 mod 4. Because if all of its prime factors were congruent to 1 mod 4, then n itself must also be congruent to 1 mod 4, which is not true because we just established that n is congruent to 3 mod 4. So n must have at least one prime factor that is congruent to 3 mod 4. Let's call that prime factor q. But since q is congruent to 3 mod 4, and we assume that this list of primes p1 and p sub n is the complete list of primes that are congruent to 3 mod 4, that means q must be one of these p sub i's in that list. But then q divides both n and the product of 4 times p1 to p sub n, which then implies that q must divide the difference between n and that product of 4 times the primes, which, as you can see, further implies that q divides 1. And that's our contradiction, folks, because 1 has no prime divisors. And so that must mean q is not part of our original list of primes, p1 to p sub n, and so our list once again is incomplete. So no matter if n is prime or composite, our original proposed list of primes, p1 to p sub n, is not the complete list of primes of the form 4k plus 3. So if we continue this logic along, we can then conclude that there must be an infinite number of prime numbers of the form 4k plus 3. Papa Euclid would be pretty proud of this proof, don't you think?